Okay, so I guess you had a chance to view and appreciate the beauty of MRI recording, right? The data that we got, and why is it that the data that you're recording, unlike other modalities, here what you're recording is actually the Fourier transform. Even though the signal is represented as S of t, the data that you're recording actually turns out to be samples of your Fourier spectra. So, it's very intriguing. So now what we will do is, as you will see here, this was supposed to be the course content and we have covered until data acquisition. We are still left with image reconstruction and image quality. We covered what we'll be covering today. It's going to be very straightforward. 10-15 minutes we'll finish image recon because there is nothing new. Okay, so how do you obtain original signal? Take inverse Fourier transform. So I'll just spend some time. So all this revision of how we do data acquisition to get rectilinear, polar, I will not spend time because that is not needed now because of the video lecture. So you can review the previous video. So where we will go is we will jump into image reconstruction. So we have two kinds of data. One is rectilinear scan, the other is polar scan. So what we've seen is acquired signal actually is, we have samples, right? You have samples of f of u comma y on a rectangular grid if it is rectilinear scan. All you have to do is just take inverse Fourier transform, 2D inverse Fourier transform, you will get your image. Likewise in polar scan, acquired data already you have f of u comma v but in polar grid. So you can either do that, you can convert the 2D to a rectangular grid and do it, or apply back projection approach. Okay, so all of this reconstruction from Fourier to image we also did for CT. So several of those algorithms can quickly guide you as to how you can do the inversion. Okay, so we tried convolution, remember. So same things can be applied here, nothing secret about it. Okay, only thing that I'll do is just refresh within our equations what we have and how we start to look at the data or organize the data in a standard format. So you acquire the data, right? In the rectilinear scan, you are having phase encoding. Phase encoding comes from gradient y. You have the area AY, right? So you are applying this gradient for a time period for phase encoding. So this is the phase that is accumulated. So you have for each phase, you have a baseband signal that you are getting with frequency encoding. So your S0 of t, this t is what? X direction, time over which you are acquiring. Essentially it translates to frequency, correct? Gamma gxt is going to give you the highest frequency in the readout direction. AY is the v direction, how you are moving in. So phase, right? So what you have is S0 of t comma frequency and phase, essentially, right? You have, this is the signal, f of x comma y e power minus j gxxt e power minus ay dy dxy. So this is the same equation we saw before. And we can readily identify, like we said, what is your u direction frequency, what is your v direction frequency. So once you have this, what you essentially have is f of u comma v is nothing but S0 of u by comma. So you are reorganizing the data, right, with this, so that you recognize what you have in this form is nothing but f of u comma v. So once you have that, take the inverse Fourier transform. This is the fundamental equation in MRI for rectilinear scanning. Similarly, what you can do is for your polar coordinates. Polar coordinates, how do you organize the data? You have to have r comma theta, or r we won't call r, we have been using rho, right? Because so in the acquired data in the polar coordinate, you acquire it with gx, gy, so that you can get different theta. So range direction we will call it as a rho. The angle is theta, correct? So essentially what we are doing here is we are identifying u as gamma gxt and v as gamma gyt. We are applying simultaneously gx and gy, and the readout is for the same duration. So here you notice v also has the t. If you understand the meaning, you don't have to pay attention in remembering all this. This will come straightforward by thinking about the physics. Using the mathematical notations, you will arrive at the equations. So U is gamma Gx T because it is a frequency. Gamma Gy is the frequency. You are acquiring it over a period T, right? T is the acquisition. So you are having this readout gradient while you are acquiring. So that's why this T is there. So this was there from before. The phase direction also in polar means you are applying gradient Gy also simultaneously. Therefore the T is here also. So your rho is magnitude, right? Square root of Gx square plus Gy square. Theta is as before, tan inverse of these two. So you have reorganized, you recognize what you are measuring is nothing but is in the polar coordinate. F of rho cos theta, rho sin theta for different rho and theta. Right. So once you have this, you can go to the time spatial domain, which is your image. Clear? So there's nothing more to add to image reconstruction with respect to MRI. If you understood the basic signal, we are already having Fourier domain of the data, 2D Fourier transform of the data. Take inverse Fourier transform. So you organize it like this. So how do we generally organize it? So it's useful to think whatever you are recording, the raw signal from each successive acquisition. So you have one setting, you acquire once. You have another setting, you acquire again, right? So you can label the readout direction is T. So each acquisition has a time. So you can think about your U is filled. Different acquisition means you're moving in space in the V direction. So you can start to think about raw signal from successive acquisition as being recorded as lines in 2D space. That is in case of rectilinear, for example, it's easy to think about it as parallel lines, right? So we call this as K space. I remember we mentioned it's a Fourier space. But in the domain, usually they, instead of talking about frequency, right? When you have cycles per second in time is frequency, correct? Or number of cycles, in 2 pi radians. But when you talk about spatial variations, not time variations, usually it is advantageous to say number of cycles over a length rather than time, right? So number of cycles, one cycle is a lambda, right? In your time domain, frequency. So number of lambdas in the length, the 2 pi length, is usually a wave number. So it is convenient when you talk about spatial frequencies. People talk about frequency in terms of K space. K is referring to the wave number. Okay, so that jargon is still there. So people, but the way we have covered, your U is Kx, V is Ky. Okay, so you just have to be careful. Whatever we are covering is correct. You just have to, if you are reading different literature from different background, they may call this as K space. Essentially, K space is similar to what you have. Just denoting it as K space because of the jargon of wave number rather than the frequency. So you align your data, time is your U direction, acquisition number is your Y. Each time you acquire, you align the data like this in your variable. So this is your 2D Fourier transform of the data. Once you have this, you grid it, take the inverse Fourier transform. Okay, so you can get your, of course the 2D inverse Fourier transform data provides spatial distribution. Generally it's a complex value and therefore magnitude is taken to provide the image. Clear? So that's it for image reconstruction. Very simple, right? You know intuitively what it is by now. So just to show another example, right? What we recorded. So this is called as K space. Nothing different from U and V that we covered. One is your frequency encoding direction. The other is phase encoding direction. Whatever you are recording, you align it like this in the variable space. Right? When you align it like this in your variable space, and then take 2D inverse 2D Fourier transform. That should be an inverse. If you do that, you get the image. Clearly, you can see this is fantastic image, but it's really complex to visualize that it is coming from this data acquisition and this data alignment. But such is the beauty of MRI that you can do several things, but to get this basic feel for what is this gray, what is this black, what does this mean, is not straightforward. I hope you repeat the physics lectures and then repeat the data acquisition lectures and get a feel for, because reconstruction lecture is straightforward. If you understand this, taking inverse Fourier transform coming here should not be that difficult to understand. Okay. So finally, last slide, what we will do is put every signal, right? We have measured all the signal, we'll put it in the equation, align it up so that we see the signal equation. So imaging equations. We know f of x comma y of t is this guy, some scaling constants, is essentially a magnetization vector from x comma y at a 0 plus, right, at the start, which is going to decay. So this is your signal that you are recording, right, in the transverse plane, right? So minus t and with time constant here. But if tr is sufficiently large, which we saw before, then no issues. This essentially becomes your m naught, that is your equilibrium value times sine alpha. But notice here, this is good. Whatever we have covered so far is good when you do it once. There is an important concept that we will reveal now. Okay, what we want to do is repeat it again and again and again, right? That is, this is your magnetization vector. I am pushing it to the transverse plane. Again, it comes back. Again, I am pushing it, repeating the experiment with the different settings, right? So when I do it like this, what happens is, we were used to the term called, allow the signal to come back to what? To equilibrium position, your m naught, right? That is what we were doing so far. So if you allow it to come to equilibrium, we were calling that value as m naught. But it so happens that if you do this multiple times, that magnetization vector never comes to equilibrium, right? You have to wait for a long time for it to come to equilibrium. But you repeat it. So what happens is, it doesn't reach the equilibrium, but it reaches a steady state. So each time you do, right, this experiment, the value that it comes ready before you do the next one, you can say that after several renditions of this, repeats of this, you will call it as steady state mz, not m naught. M naught is equilibrium, which happens when you wait for long time without multiple push, it comes to equilibrium. The moment you are going to do this pushing experiment several times, repeating the sequence several times, you are pushing this vector, and as you know, every time with any displacements, right? When you do this in dynamics, it has to have some steady state. You do this multiple times, right? Static dynamics. So when you try to push this several times, you will have reach a steady state. That mz is not equilibrium, but it is a steady state. So now we will just rewrite our equations to correct for this. If you are going to repeat the experiments, right? Repeat the acquisitions. So let the steady state value, we'll denote it at mz at infinite, comma x, comma y. So we are using this jargon. Instead of 0, we are putting infinity. Then what happens is your mxy at 0 plus is not m0, right? This is what we said before. But now it is mz, wherever you are starting, mz, the steady state value, not the equilibrium value. So your m naught gets replaced by mz at infinity, x comma y, sine alpha. So once we can show that this essentially what this mz is your equilibrium value with some duration. The duration has to do with number of times you are repeating and the properties of how long you wait, which will dictate your T1, right? So T1 constant, T1 property of the tissue, and how far you wait, your TR, this relative TR to T1 is going to have some duration of your equilibrium value. So you are going to end up using mz, the steady state value in the imaging equations instead of equilibrium value. And therefore your f of x comma y of t is nothing but, you substitute, right? You substitute the values, you get a m naught x sine alpha e power whatever times this guy, right? So which we can directly say this m naught was proportional, right? So it can say it's proportional to proton density sine alpha, this guy. So when alpha is also pi by 2, which is your maximum signal, then you get f of x comma y is proportional to this guy. Okay, so this is your imaging equations. This is modified. This is your f of x comma y, meaning what is your f of x comma y comma t? This is the image, right? At every pixel x comma y, this is your image. At every pixel x comma y, your basic signal strength is dependent on the proton density at that location. but it is also dependent on the T2s and T1s and the time to repeat. All that is going to, so we saw in contrast mechanism, right? How do you play with this to get a differential weighted images, right? That is our f of x comma y comma t. This is a governing equation. Depending on how you combine T2, T1, TR, you get different weighted images. Okay. So of course in spin echo we measure TE is far less than T2. Right? We repeat the experiment. Clear? So this completes in some sense the image formation. We need to next study about image quality.